Okay, hi everyone. Here we are here with a question, SJPO 2016 Q5. Okay, so we're given a train and a certain mass. The mass is given, and it's traveling down an incline of 2 degrees. So there's a train, it has wheels, the incline is 2 degrees, right? And we're given that it's traveling at a constant velocity v. So I'll just denote this v, and do note it's a constant velocity, right? That will be important soon. And it's also expending a power of 60 kilowatt. Okay, so first of all, we need to consider the force body diagram on this train, right? So what are forces acting on this train? So I'm going to draw the forces in red, right? So first of all, there's always gravity, right? There's always the mg, and there's also normal contact force, right? Between the train and the ground, n, right? And the normal contact force, right? Okay, let's list down all the forces first, okay? Then next, there's also going to be the force exerted by the wheels on the train. So I'm going to write this as F wheel, okay? Exerted by the wheels on the train, right? So the wheels are the one that are trying to push the train forward, right? And lastly, there's also friction acting, friction or drag of sorts, right? And in general, there's a bunch of sources of friction, such as uh, friction between the crankshaft and the wheel, friction, rolling friction, or even air drag, right? But in general, I'm just gonna generalize. I'm just gonna lump them all together, and call it drag, right? So drags includes friction in this case. In this case, I'm including friction, right? Friction is included in this drag force. I'm lumping it all together, and we'll see that this lumping is justified, right? So okay, so what can we deduce from this force body diagram? First of all, do note that the the drag and the wheel, the driving wheel, right? They are parallel to the slope, right? And there's another parallel component, right? Gravity has a parallel component also. So if I break down gravity into a perpendicular component, right, which I'll highlight in yellow, and a parallel component which I'll highlight in orange, right? Gravity, the weight, gravitational force, right? The weight of the acting on the train by Earth, right? Breaks down into two components, and it's going to be accordingly, right? The yellow is going to be mg cosine theta, and the orange component parallel will be mg sine theta. Okay, you can always check that this makes sense in the extreme limits, right? So that when theta equals to 0, then we have mg sine theta equals to 0. That makes sense because if you're parallel horizontal, right, the train is horizontal on level ground, there's no gravity doesn't pull it along the track. So whenever you're confused about cosine and sine, you can always think of the two extreme cases where theta is equals to 0 degrees and theta equals to 90 degrees, right? These generally will help you do a very quick sanity check on this, so that you would, if you're not confident of your angle chasing. Okay, so anyway, um the first thing we observe is that in the perpendicular component, right, the perpendicular component is such that there is there is no net perpendicular component. So perpendicular, right, the net force must be 0. If not, the train will be sinking into the slope. So we must have that perpendicular component. You must have that the perpendicular component as a net force of 0. So that gives us n minus mg cosine theta equals to 0, right? Or n equals to mg cosine theta. And generally, right, when you do a lot of these questions, eventually you learn how to focus on the more important forces, right? When if you're experienced enough and you see this question, you probably wouldn't even draw the n, and you probably would just draw mg sine theta, right? You learn how to do this kind of deduction, yeah, very quickly, and so you wouldn't waste much time on it. But I'm just trying to spell it out here, be absolutely clear that yes, normal contact force is a force acting on a train, but is balanced out by, normal contact force will always adjust to balance out the perpendicular component of gravity. Okay, so anyway, that aside, right? Now we can focus on the parallel components. Okay, so what does the condition of constant velocity tell us? The condition of constant velocity tells us that there's no net force, right, acting on the train. And so this might seem weird, right? Why aren't we trying to drive it with the wheel? There's gravity. Why is there no net force acting on the train? And the reason is due to drag, right? Drag, it, initially, if the velocity is zero, right, drag is zero, so the train accelerates faster and faster, right? Accelerates downward, right? But as soon as the velocity reaches high enough, right, the drag is going to be significant enough such that it perfectly balances out the wheel plus the gravitational force parallel, the parallel component of the gravitational force, right? And it's going to balance it out so that the train doesn't accelerate in the parallel component anymore. So what we have is that we basically have F wheel plus mg sine theta, right, minus F drag equals to 0. And rearranging this, right, we know that we can get that F wheel equals to F drag minus mg sine theta. Okay, and why do I want to do this? It's because we can now link it with the power. The power is 60 kilowatts, right? 60 kilowatts of power needed to travel down the incline. So you may be wondering, wait, aren't I on an incline, right? How come if I'm on an incline, why must I still exert power, right, to move it down? Why can't I just let gravity do the work? And the answer is that yes, if you let gravity do the work, you can move forward, right? But your velocity will probably not reach 10 meter per second, right? Your velocity will probably be like 0.1 meter per second, right? It's the 2 degree incline, just going down very, very, very slowly. Yes, sure, that works. But if you want to have a terminal velocity of 10 meter per second, right, then you need to put in some amount of power, right, to overcome the drag force, right? So what this tells us is that F wheel, right, times V, right? Okay, so strictly speaking, power is equals to power is given by force dot, right, dot product. This is a dot product velocity, right? Yeah, this comes directly from work equals to integral of force dot dx. Okay, so this comes directly from it. If you differentiate both sides by time, you get this. Okay, so power equals a force dot velocity, but you see that this is a dot product because the force and the velocity are vectors, right? So maybe the force is in this direction, velocity in this direction, right? Maybe it is perpendicular, then the dot product is 0, even though they're both non-zero length, right? So remember, vectors have magnitude and direction, so this is a dot product here. Yeah, dot product cares about the direction they point in. So anyway, where this is, truly speaking, is a dot product, but because the velocity in this case is parallel to the wheel, right, it's just F wheel times velocity V. Okay, and so this, we know that this is the power 60 kilowatts. 60 kilowatts. Okay, so with that, how do I calculate? Okay, so 60 kilowatts equals to F times V, and if we multiply it out, this is F drag minus mg sine theta times V. Okay, so that's what we have right now. Let me just move this working to the left a little bit. Okay, so with that, this is if the train is going downwards and incline, right? Down and incline. But now the question asks, well, how much power is required for the same train to travel up the incline, right? At the same constant velocity. So basically, what has changed over here is that now instead of going down the incline, if we're going up the incline, then what does that look like? Right? So now the same incline, angle theta, the same train, right? The wheel will be different. So I'm gonna call it F wheel, F prime wheel, right? Prime meaning in the second scenario, right? So F prime wheel is not the same as F wheel, right? It's a different force, right? Because now we're trying to go upwards, the incline, right? And so there's still gravity, right? Gravity still stays the same, and there's still the normal contact force. And we know once again that basically the normal contact force is always going to balance out gravity so that the train doesn't sink into the ground. So we can effectively reduce gravity, right? I'm just going to take a shortcut and just going to write mg sine theta over here, right? To mean the gravitational force, right? And of course, there's also the drag force, and F drag, right? I'm going to first say F drag prime, but you realize that what does the drag force depend on? Drag force depends on the friction between the wheel and the ground and the velocity you're traveling at, right? Because in general, drag is dependent on the velocity. But in this case, if you're traveling at the same constant velocity, right, then the F drag must be the same. So this F drag, right, in the second scenario, when you're going uphill, the drag that's trying to prevent you from going uphill is actually the same drag force as this drag force in the first scenario when you're going downhill, right? So basically, I'm now asking, right, F wheel, I'm asking what is F wheel prime times V. Okay, I'm asking what is this quantity, right? And we can balance out forces again, right? So when terminal velocity, we have F wheel prime equals to F wheel prime minus mg sine theta minus F drag prime, right, which is equals to F drag, so same thing, is equals to 0. And realize that now F wheel prime is equals to F drag plus mg sine theta. Okay, so the difference right here is that previously we had F drag is equals to, previously we had F wheel is equals to F drag minus mg sine theta. Now we have that F wheel prime is equals to F drag plus mg sine theta. And the difference is because previously we're going downhill, we had gravity trying to help us, right? Previously, if this gravitational force is a huge quantity, then the wheel will not need to do that much work, right? So if this increases, this decreases. But in this case, we're actually working against gravity. So if gravity somehow increases, if let's say the mass increase, then our force that the wheel needs to act, right? The wheel needs to exert to drive the train up that slope would increase. So using this kind of intuition, right? Using this kind of arguments where you look at the expression, you think if the gravity increased, right? What would the wheel need to do? How much would the wheel need to compensate for it? That helps you quickly verify the formulas that you have arrived at. So, okay, so F wheel. So now all that remains to do is to substitute in these values. So to calculate F wheel prime times V, right? We just substitute this in and realize that it is F drag plus mg sine theta times V. And this, okay, so right now we don't know F drag, right? That nowhere in the question did they give us F drag explicitly. But we actually do not need to know F drag, right? Because we actually only need to know F drag times V, right? F drag times V, and we can actually calculate F drag times V by looking at this expression. We know mg sine theta, right? We know V, so we know the left hand side is F wheel, so we can calculate F drag times V, right? But actually, we can take a shortcut even, right? We can take even a bigger shortcut and say that, hey, this is just F wheel times V plus 2 mg sine theta times V, right? Because this was a minus, now it became a plus, right? This was a minus, now it became a plus. So just plus 2 mg sine theta, right? And we know the first quantity here is 60 kilowatts, right? So all we need to do is calculate the second quantity. And the second quantity, we have all the values we need, right? So m in this case is 7 times 10 to the 4 kg, right? G is 9.81. Sine theta is sine 2 degrees. And V is 10 meter per second. Right? So we just need to put in those values. And what we'll get is, let me just punch the calculator. 7 times 10 to the 4 times 9.81 times sine 2 degrees times 10 meter per second times 2. Okay, so what we get is 479 kilowatt. Okay, approximately there to 3SF. Okay, and this, if we add it to 60 kilowatts, right? 479 plus 60, that'll give us 539 kilowatts. Alright, so the closest answer in this case is A, so the answer is A. Okay, so I hope that this question has been clear, and basically the key takeaway over here is that I think the key takeaway over here is that we can stare at the expressions we get, right, from the math, and we should try to have an intuition for what the expression is saying. In the first scenario where the train is going downwards, the expression over here is saying the wheel has to work as hard as the drag force minus the gravitational pull, right, the gravitational force. So that would imply that if the gravitational was stronger, right, then the wheel will have to act less, right, because there's a minus sign over here. You minus a bigger number, then the left hand side would drop, right? And that makes sense. It makes intuitive sense because the stronger gravity is, the less hard, right, the wheel will have to work to overcome drag, right? And in the second scenario, we see that it's a plus sign, meaning that the stronger the gravity, right, the harder the wheel will have to work. And that also makes sense. So I think that's the key takeaway from this question. Otherwise, the math is rather simple. They're just balancing forces, and yeah. So always try to have a physical intuition for the things that's going on in your question, and yeah, try to see beyond the equations. So if not, I hope you have enjoyed this video. I'll see you in the next one.